Friday at noon. All right, well, without much further ado, I'm thrilled to roll out the latest episode of the Quantum Live seminar series dedicated to the research and academic communities. The seminar takes place every Friday at noon Eastern Time and will be hosted on the Qiskit YouTube channel. And I'm delighted to see so many of you tuned in already. Today, I have the pleasure and delight of hosting Bharath Kannan from the Engineering Quantum Systems Group at MIT, who will talk about waveguide quantum electrodynamics with superconducting artificial giant atoms. And hello, Bharath, how are you?
Doing great. How are you, Zlatko?
Great. Thanks for accepting the Facebook invitation. It's a pleasure to see you again and pleasure to have you here. Where are you tuning in from today?
Yeah, I'm in from Massachusetts.
Awesome. Well, while we get all set up, let me give a bit of background. Bharath received his bachelor in physics from Rutgers University in 2016. Bharath is currently a graduate student in the Engineering Quantum Systems Group with Will Oliver and Simon Gustafson at MIT, where his research focuses on microwave quantum optics and waveguide quantum electrodynamics with superconducting circuits. Bharath is also a recipient of the NDSEG and the Jacobs Presidential Fellowship. So Bharath, I will turn it over to you and interrupt you with questions from the audience during the talk. So take it away.
Thank you so much, Zlatko, and thanks again for inviting me to come and give a talk here. So I'll be talking about some of our latest results that was just published a couple months ago on Waveguide QED with giant atoms. But before we dive into that, I kind of maybe want to say, one of the motivating principles behind this work was to try and consider some novel regimes of light matter interactions, which perhaps are relatively simple to implement using superconducting circuits, but maybe not so much with other types of atomic modalities, be it artificial or natural. And so in that sense, I would say both this waveguide quantum electrodynamics architecture and this notion of a giant atom, which I will more rigorously define later in the talk, they both fall under this kind of a category. And to, again, take a step back and kind of enjoy this nice picture that we have on the title page, what you can see is that we have two transmon qubits, which will act as our artificial atoms. And they're coupled to this meandering transmission line, which is the waveguide in Waveguide QED. And what we're going to show is how we can kind of use this sort of an architecture to have these atoms coherently interact with each other with high fidelity. But before we get to that, I want to talk a little bit about architectures in quantum electrodynamics. And the first one being something that most of us may be already familiar with, cavity quantum electrodynamics, or circuit quantum electrodynamics if implemented using superconducting circuits. And to briefly describe what's going on here is, you have some atomic degree of freedom, which is strongly coupled to the discrete modes of a cavity or a microwave resonator. And this has truly become the dominant architecture for modern superconducting quantum information processing, but also in other modalities as well. For a wide variety of reasons, but maybe a couple would be the first, that the cavity acts as a protection against dissipation into the open environment to which the cavity is coupled to. And additionally, we're able to use this cavity QED architecture for coherent single and multi-qubit quantum operations, as well as quantum measurements of the qubit or atom as well. And so putting all of these pieces together, you have the recipe for a potentially successful implementing quantum information processing. Now, waveguide quantum electrodynamics contrasts quite nicely to cavity QED, I would say, in the sense that as opposed to trying to protect your qubit or atom from dissipation, the qubits are instead directly coupled to an open environment, that being the waveguide. And as a result, this is a platform that is potentially ideal for studying dissipative phenomenon, as well as being able to take advantage of quantum interference between photons in the waveguide to do some certain tasks, which we'll see later in the talk. And additionally, this kind of an architecture is potentially interesting in terms of performing some kind of quantum simulations of purely open quantum systems, but maybe more so on the quantum information side of things. Waveguides are likely necessary in some capacity in order to route quantum informations between quantum processors or nodes in a quantum network. And so we can think about trying to use this kind of an architecture where your qubits are directly coupled to this open environment in order to implement some kind of quantum interconnect. But it turns out that this sort of architecture can also be used for microwave photon detectors. So for those of you who follow this seminar series closely, you may have seen a talk by Alexandre Blay on microwave photon detectors. And indeed, the device that he presented in that talk, the principles of operation are based on waveguide quantum electrodynamics. So there are quite a few interesting applications to be had in this kind of an architecture. And so to get a bit more specific, when we try and implement this waveguide QED with superconducting qubits, essentially what we're doing is we're taking artificial atoms and coupling them to 1D free space. So in our case, we'll be using transmon qubits. They're one of the simplest superconducting qubits that you can use, and they're going to be placed along a transmission line, which will serve as the waveguide. And this is a very nice platform to do some interesting microwave quantum optics experiments. But one question that sometimes I get asked is, why do waveguide QED with superconducting qubits? What's the advantage to be had there? And the primary one I would say is superconducting circuits give us access to some interesting regimes of this model that are otherwise difficult to implement in other platforms. And specifically, I'm talking about getting strong light matter interactions between the atomic and photonic degrees of freedom. And this is what really lends itself to then being able to implement applications of this architecture. But on top of that, we can lithographically engineer and scale our devices. And we also have a certain degree of in situ control over the atoms. Specifically, we're able to control the frequencies of the qubits and therefore the electrical distances between for photons between qubits along the waveguide. And so this is some nice features that our superconducting qubits have. And then additionally, because we're in this strong coupling regime, we are able to have the waveguide mediate qubit-qubit interactions, which is, again, something that might be of interest. And so when we think about applications, maybe one of the more obvious ones, because we're coupling to this open degree of freedom, is using this sort of an architecture to generate non-classical and entangled itinerant or propagating photons, which can then be applied towards quantum communication protocols. And we can also think about trying to use these waveguide-mediated interactions for long-range interactions between qubits, which can be applied in maybe quantum simulations or computation itself. And so the next question is, what are the challenges that one typically has to deal with when dealing with waveguide QED? And I would say the primary one would be the fact that because the atoms are strongly coupled to this open dissipative environment, your qubits are always subject to dissipation. And when we want to do tasks, for example, that don't involve dissipation, like initializing the qubit, that can prove troublesome. And so what we want to think about is it possible to kind of come up with a way of having a tunable coupling to the environment that I care about? And then another question is it possible to kind of engineer these interactions, which are mediated by the waveguide, tailored to kind of how we want it to be, how we want qubits to interact? So these are two challenges that I'm going to show how giant atoms can address. And so to kind of give an outline for the talk, it's going to be split into two parts. The first one is going to be talking about the physics of waveguide QED in general. And I'm doing this because I found that even within our community, while people are very familiar with cavity and circuit QED, people aren't as familiar with the types of phenomenon that occur in waveguide QED. And so we will kind of go through what we can expect in this type of a system first. And then after that, I will talk about how giant atoms come into the picture. So to begin, let's get a bit more specific and talk about how this sort of an architecture is modeled. So in our devices, we typically have these transmon qubits. They're flux tunable. So there's a squid in which we can thread a magnetic field to tune the qubit frequency. And they're capacitively coupled to a 50 ohm transmission line, which serves as the waveguide. And so if we write down the Hamiltonian for this system, we can first write the electromagnetic and atomic Hamiltonian separately. And we note that, because this is a transmission line that's open on both ends, we have both left and right propagating photons, and it's a continuum of modes, which is why we have this integral, and then we just have a standard sigma z Hamiltonian for the qubits. Now, the interaction between the qubits and the transmission line is implemented via this capacitive coupling, and it's a transverse interaction in the sense that if we apply or if we provide photons into the waveguide that are resonant with the qubit, this can then be used to excite the qubit. Or alternatively, if the qubit begins in an excited state, this qubit can then emit a photon into the waveguide, which will propagate away. And I've been mentioning this notion of strong coupling regime. So to rigorously define that, essentially what we're talking about is where the coupling rate or the emission rate of the qubit into the waveguide is much stronger than all of the other decoherence channels in the system. So dephasing of the qubit or non-radiative decay into other modes that are not the waveguide. And so this is the regime that we want to be in order to kind of see the physics that we observe. And this decay rate can be kind of calculated in terms of both the coupling to the waveguide itself, as well as the density of states in the waveguide. And so
maybe,
sorry,
maybe before jumping to the next step,
yep.
To also get everyone on the same page and help me understand the coupling term here. So the A left, those are all left propagating traveling photons on the transmission line.
Yes.
In the absence of any transmon there, so the sort of uncoupled basis.
That's correct.
A dagger, right? So the first one is just, how many photons left going and right going do you have? The second one is the atomic Hamiltonian. Now the coupling has the ability to emit a photon either going to the left or going to the right, but with the same amplitude, right? So there's no asymmetric emission of left versus right. There's no helicity.
Yes. Well, there's a bit of subtleties which I'll get into in the later slides, but yes, you can think of it as just emitting symmetrically in most cases.
Mm-hmm. Okay, right. And so xj is the position here of the atom, v is the velocity of the traveling wave on the transmission line, and
yep.
And so can you say a little bit more about how capital J sub little j of omega gets determined?
Yes, so this is ultimately determined by the kind of the capacitance. It's the matrix element that's formed between the qubit and the waveguide. So you can think of it as kind of a dipole, electric dipole coupling operator. So we take the dipole of the qubit and multiply that by the vacuum electric field of the transmission line, and this will give you the strength of the coupling, J sub j. Right. But to get the effective emission rate gamma, you then have to include the density of states D of the waveguide. So you can think of this as kind of a Fermi-Golden rule.
And wouldn't we expect the density of the waveguide, in the absence of the qubits, to be flat?
So it would be an ohmic spectrum, typically. But you can, in general, you could also have a waveguide with structure or with dispersion, right? And then that would kind of change the density of states as well. For example, if you had some kind of band gap, that would change these. But in our case, we're dealing with just ohmic path. Okay, awesome. Yeah, so that's just to be more general, but it's probably in the flat regime here, or linear. Linear. Yeah, linear. Okay, good. Awesome. Thanks. Okay. And I guess to make one more comment, which will be more relevant in the later slides, but you'll notice that this interaction Hamiltonian has a dependence on the position of the qubit. And so what we're going to find, and this position is x sub j. So what we'll actually see is how the physics of the system changes depending on what the spacing between the qubits along the waveguide are. This is something that we will talk about.
Yeah, I guess it's maybe also interesting to note that this is a little funny in a sense, right? Because the A of omega, those are non-local waves, right? I mean, those are discrete operators, if I understand correctly.
Right. This is in momentum space or frequency space. Yeah.
Right. So while the interaction is local, you've now sort of moved in the Fourier domain here, and so you get this non-local interaction. But I guess you're going to lead into that.
Yes. And so, yeah, to kind of, well, I guess this leads me into my next point quite nicely, in the sense that looking at this Hamiltonian, it's a little bit of a beast to deal with in terms of performing calculations. And so typically what we do is we introduce this thing called a master equation, which reduces the dynamics of the system into a part which just involves qubit operators. This is the coherent part given by this H tilde, as well as a part which deals with kind of the dissipation that's induced due to the coupling to this continuum of modes in the waveguide. And this, doing calculations with these master equations, is a bit less unwieldy. But we can actually break down this master equation even further to kind of think about what are the phenomena that occur. And so if we take a look at first this part which accounts for the dissipation, you can see that it's a sum over two terms, j and k. So it's just summing over all of the qubits in the system. And so when j equals k, so this is talking about the same qubit, that term will describe the single qubit dissipation into the waveguide. But it turns out that you can also have terms that correspond to j not equal to k, so between different qubits. And this is actually some kind of correlated dissipation. So your dissipation actually has correlations involved. And we'll talk about that in more detail in a bit.
And maybe a quick question about the so this Lindblad equation is in the Markov approximation. So
yes, so this is assuming a Markovian environment, in the sense that the emission rate of the qubits into the waveguide is much slower than the travel time for photons between the qubits. That is the regime that we're in. And okay, yeah, and then we can also take a look at the coherent part of this master equation given by this Hamiltonian, reduced Hamiltonian, which includes kind of two interesting terms. Well, the first one is just the natural qubit Hamiltonian, but the second one is essentially this waveguide-mediated qubit-qubit interaction that I've mentioned. And then we can also have a term that represents the, for example, if we apply a classical drive into the waveguide, what that has, or how that acts on the qubit as well. And so kind of in this first part of the talk, I'm going to be discussing each of these parts individually, in a sense, and we'll see what types of physics come out of that. But before we do that, it's kind of nice to just go through a quick survey of works in Waveguide QED and microwave quantum optics. So actually, this whole notion of coupling qubits to a waveguide in superconducting circuits started when, in 2010, when I think it was a flux qubit was coupled to a microwave transmission line in the strong coupling regime, so the regime that I just mentioned in the previous slide. And essentially how they measured this was you just take spectroscopy of the qubit, and it turns out that when you're in this regime, the qubit is a mirror to single photons. So if you apply a weak enough coherent tone and measure transmission, you'll see a dip in transmission at the qubit frequency. So that's what they observed here. And then people also went on to go to the ultra strong coupling regime, where the coupling strength is now almost on the order of the qubit frequency. And there was also some work on, in general, measurement techniques in microwave quantum optics. This is done by Christopher Eichler in the group of Andreas Wallraff. And that was mostly work with just one qubit, but there's also been some literature on multi-qubit devices in Waveguide QED. So the first kind of demonstration of these waveguide-mediated interactions was done again by the group of Andreas Wallraff back in 2013, a few years ago. And people have also started to take that further. So I've just mentioned that these qubits can be used as single photon mirrors. So people actually have thought about creating cavities out of these single photon mirrors, which are the qubits. And I guess a little bit of a shameless plug for my other work. I mentioned that Waveguide QED can be used to generate non-classical photons. So we actually have a paper coming out in Science Advances next week that will show how you can generate spatially entangled itinerant photons in Waveguide QED. So this is kind of the types of works that have been pursued in this field. So the simplest experiment that you can do in Waveguide QED is spectroscopy of the qubit. So this is along the lines of that first experiment I had in the previous slide. And essentially what it involves is applying just a coherent tone into the waveguide. And this coherent tone will, if it's resonant with the qubit, will excite the qubit from its ground to its excited state. But we also know that the reverse process will occur. If the qubit's in an excited state, it will also emit a photon. And so when you add up these two processes of both the coherent tone being supplied into the waveguide and the emission of the qubit, it turns out that you get perfect reflection. So you get destructive interference in the transmitted wave, and you get reflection of this tone that you supplied. So this is basically this mirror behavior that I mentioned of the qubit. And you can go ahead and actually measure this in spectroscopy. So here we're just showing a very basic scattering measurement, S21, so just looking at the transmittance, as a function of the detuning between the supplied tone and the qubit frequency. And indeed, what you see is when the tone is resonant with the qubit, this transmission is very highly suppressed. And you can actually go ahead and do this as both a function of the detuning between the drive and the qubit frequency, as well as the power of the probe that you supply. And indeed, because our qubit is quantum nonlinear, we kind of expect to see some sort of saturation when the drive power gets too strong, such that you're going beyond the single photon limit. This transmittance starts to get closer and closer to 1, and indeed, that's what we see in this vertical line trace of the transmittance S21. So you can see that it goes from 0 to 1 as we increase the probe power.
So quick question here. So I guess the curve on the bottom left, that's the same thing you would get for just a classical resonator, right? And then the 1 photon power should be somewhere around minus 125 dBm?
It depends on the coupling to the waveguide. So I think in this particular device, it was around the minus 140 dBm, 130, 140, because the coupling here was very strong.
I see.
Yeah, and so indeed, as you mentioned, this is the sort of behavior that you would expect for a classical resonator, but the key difference here is the nonlinearity of our qubit means that this feature becomes saturated as you increase the probe power. Good. So that was kind of looking at things in the frequency domain, but you can actually think about measuring these photons in the time domain. In particular, you can actually do a bit of calculation and find that there's an input-output relation where the state of the photons at the output of the device will clearly depend on the initial state at input, but it also depends on the state of the qubits and their position along the waveguide. And so you can think about trying to use these equations in a clever way by initializing your qubits into some interesting state such that you're able to generate some interesting state on the right and left propagating output nodes of the device. And kind of, did you have a question?
Yeah, you might be getting to it, but I was going to just say, yeah, how from these equations you figure out all the issues with all the possible backscattering and forward scattering between the emitters, because the second emitter can scatter back to the first, which can scatter to the second, or all this. But maybe you'll get into that.
Right. So I guess to quickly comment on that, essentially these output modes will depend on the state of the qubit, which is given by this lowering operator sigma minus, and clearly this is a time-dependent operator. And so when you kind of do the calculation in the master equation, all of those phenomena are kind of accounted for in that term. Yeah. And so the simplest example of showing how these qubits can act as nice quantum emitters would be to just take a single qubit and couple it to your transmission line. And now, as a proxy for measuring these annihilation operators AR and AL, you can just measure the voltage at your digitizer. These two values are related to each other as a function of time. And you can, for example, think about preparing your qubit in a 50-50 superposition of the ground and excited state. And indeed, what you see in that emission process, so this is just looking at one side, you can see the photon come out in the oscillations which are at the qubit frequency in the digitizer voltage. You could also think about, for example, fully exciting your qubit to the excited state. But actually, in this case, because when we measure this voltage, we're averaging over many repetitions, because we've initialized the qubit fully into its excited state, it'll emit a Fock state, a single photon, which gets emitted with random phase, right, uncertainty principle. And so when we average over many repetitions, it actually averages to zero. And so in the voltage, you won't actually see a signal. You'd have to look at the power. Alternatively, okay, you could prepare the opposite 50-50 superposition, and indeed what you get is a photon or half a photon that comes with the opposite phase. And so this is just to go and show how you can actually use these qubits as emitters of photons into the waveguide.
And quick question, what sets the frequency here between the oscillations?
Yeah, so the photon will be emitted at the qubit frequency, but we also do down conversion so that we can measure it in the digitizer, because our digitizers have a finite bandwidth, I guess, like 500 megasample or 1 gigasample, and so we can't measure at several gigahertz. And so what we do is we down convert the signal to say 40 megahertz or 20 megahertz, and then that's the oscillations that you see here.
Mm-hmm, mm-hmm. Mm-hmm.
Good. Yes. So now that we've kind of looked at a couple of single qubit phenomenon, the next thing to do would be to think about what happens when you have multiple qubits coupled to a waveguide. And again, the simplest non-trivial case for this is just 2 qubits. And in addition to that, we're going to consider the case where these 2 qubits are separated by 1 wavelength, where this wavelength is determined by the qubit frequency. And the 2 qubits here are assumed to be on resonance with each other. And furthermore, let's say that the initial state of the qubits is EG. So the first qubit's excited and the second qubit is left in the ground state. So let's think about what might happen here. So we've excited the first qubit, but it turns out this waveguide essentially kind of acts as a beam splitter for these left and right propagating modes, as Zlatko alluded to earlier. And so if we just let this system evolve, what you'll see is the qubit just emit a photon into half a photon on one side and half a photon on the other. Similarly, if you excited the second qubit instead, you would get the exact same behavior. So this would just beam split the photon that comes out between the 2 left and right propagating modes. And so there doesn't at first seem to be anything too interesting going on here. But it turns out that if you now consider the case where you have prepared or initialized your qubits into this symmetric entangled state, so EG plus GE, well, okay, we now have our 2 qubits and they're still separated by 1 wavelength. But let's say that the left qubit was the one that was doing the emission in this state. In that case, the photon that comes out would look something like this. So you can see that you have a peak at qubit A, and then because it's 1 wavelength, you have another peak at qubit B. Or you could consider the photon if it came out of the other qubit, right? Because these are entangled. But because the separation is, again, 1 wavelength, this photon actually looks the exact same. So you have a peak at qubit B and you have a peak at qubit A. And as a result, you actually get this state has constructive interference between these 2 emission processes. So the emission from EG and the emission from GE both constructively interfere. And this leads to a phenomenon known as superradiance. So what that means is this state will actually emit into the waveguide at a faster rate than the product states EG or GE would individually. You can also consider the kind of the opposite case, where now the 2 qubits are initialized into this antisymmetric entangled state, so EG minus GE. And again, this first qubit will, if that's the one that's doing the emitting, will have a photon come out that looks something like this. But because of this minus sign in this state, if the photon is emitted from the second qubit, it's going to come out with the opposite phase. And so now we actually get destructive interference between the photons that are being emitted from these two qubits. And this leads to a phenomenon known as subradiance. So it turns out that this state actually decouples from the waveguide and will not emit into the transmission line if you're able to prepare it. And so just to kind of summarize these two results into this level diagram, so if we consider the symmetric state, I told you that this would emit with a faster rate. It turns out that it will emit with a rate of 2 gamma. And so we call this the bright state because it emits with superradiance. Alternatively, the dark state or the subradiant state, because it is decoupled from the waveguide due to this interference process, there is no emission that goes down this pathway. So that's why we call it the dark state D. And so you can actually now consider a kind of a little bit of a different configuration where instead of the qubits being separated by 1 wavelength, they're now separated by half a wavelength. And you can once again play the same game, except in this case, you're going to flip the roles of the super and subradiant states. So now because the qubits are separated by lambda over 2, which is a pi phase shift, the symmetric entangled state is now the subradiant state, and the antisymmetric entangled state would be the superradiant state. And so this would be the decay pathway. And so the roles of the bright and dark state get flipped. And indeed, this was what was measured by the group of Andreas Walraff back in 2013. They basically measured this system in spectroscopy. And what they saw was when they were at this super subradiant condition, when they measured the scattering reflected transmittance in the transmission line, the line width that they measured doubled, corresponding to this 2 gamma that's associated with this bright state.
And yeah, this is very cool. And quick question. So what happens in these pictures if we replace, like in the first picture, the qubits with, say, 2 oscillators, right? And if I have 2 oscillators, I guess I can think of maybe a common and a differential mode again. Would I be able to make an analogy like this? Or, you know, I mean, that gets more complicated here because of the entanglement, obviously. But
right. So I would say the analogy holds in the sense that if you're able to prepare, so for a classical or for a regular harmonic oscillator, like 1, 0 and 0, 1, if you're able to prepare these states with these symmetries, the same analogy would hold. I guess the main difference here is because our qubits are nonlinear, that's what would allow you to prepare this state. You need some sort of nonlinearity to do that. Good. Yeah. So all of this is essentially what we call correlated dissipation. So there's actually correlations involved in how the dissipation occurs, precisely because basically depending on which entangled state you're in, the dissipative process changes. Now, I also mentioned that these waveguides can mediate coherent interactions between the waveguides. So let's, again, consider how this can happen. And so we return to our original configuration with the 2 qubits that are separated by 1 wavelength. And it turns out that you can actually separate the continuum of modes in the waveguide into 2 groups. So the first group would just be kind of real photons, which are those that are at the qubit frequency. And these are the photons that will actually mediate the decay of the qubit into the waveguide. But you also have these things called virtual photons. So these are photons which are not at the qubit frequency. And it turns out these are the photons which will do the mediating for this qubit-qubit interaction. They'll essentially give us an exchange interaction between the 2 qubits. So if I put an excitation in 1 qubit, that should swap between the 2. However, it turns out that for this specific distance of 1 wavelength, you get
question here. At this stage, we've assumed the qubits are at the same frequency.
Yes. So in all of these considerations, we're assuming the qubits are resonant. That's correct. And so it turns out that for the spacing of 1 wavelength, the contribution to the this virtual exchange interaction that is mediated by the red detuned photons, so those that are less than the qubit frequency, actually destructively interferes with the contribution from the blue detuned photons, so those that are higher than the qubit frequency. And so as a result, the net interaction strength between these two qubits at a one wavelength spacing is 0. However, you can, again, change the distance between the two qubits. And now let's say our two qubits are separated by 3/4 of a wavelength. So once again, we have the same consideration where real photons, which are photons at the qubit frequency, again, both qubits are resonant. This is what will mediate the decay of the qubit. And we also have these same virtual photons because we have a continuum of modes, which will mediate some kind of an exchange interaction. But with this distance, it turns out that you get constructive interference between the red and blue detuned virtual photons. And so you actually end up with a finite net exchange interaction between the qubits. And so you can actually go through and perform the kind of a rigorous calculation of this. And what you'll find is that indeed the exchange interaction, the net exchange interaction between the qubits does depend on the qubit separation, delta x, as we suspected. And in particular, it depends as the sign of that separation. And so if you simplify this 2 pi delta x over lambda, where delta x is the spacing between the qubits and lambda is this wavelength, it essentially goes as the sign as the phase difference for photons between the qubits. And so this is basically how the waveguide can actually mediate interactions between the qubits, and in particular, how it does so in a way that depends on the spacing between the qubits along the transmission line. And so with that, you can now consider, what are some of the research directions which kind of take advantage of these phenomenon that I've just shown you in Waveguide QED. And there's two questions that I typically like to ask myself. So the first question is, how can waveguides be used as a resource for qubits? And as an example of some solutions to this question, this would be things like trying to take advantage of this correlated dissipation or trying to use this waveguide-mediated interaction in some interesting way. But alternatively, you can also ask the question, how can the qubits be used as a resource for waveguides? And this solution to this kind of a question falls more under the lines of, for example, using the qubits to generate some kind of non-classical itinerant photon with some interesting state that can be applied for example, quantum communication. But really, although these two questions seem somewhat orthogonal to each other, they're really kind of two sides of the same coin, in the sense that the answers to one and the solutions to one can be applied to the benefit of the other. Now, for this work, we're essentially going to be focusing on the first question. So how can the waveguide actually be used as a resource for the qubits? But it's important to kind of keep in mind that this isn't kind of a closed question, in the sense that the solutions that we present here can be applied to the other. So with that, we've now kind of discussed the physics of Waveguide QED, and now we can get to more of the exciting stuff in terms of how giant atoms can help us address some of the challenges that I outlined in the beginning of the talk with Waveguide QED. But before we talk about giant atoms, it's useful to define what a small atom or a regular atom is. And so when we're dealing with these light matter interactions, usually the length scale associated with the atom, which is you can think of as, say, what the distance scale of the associated wave function of the atom is, or the electric dipole of the atom, what that distance is compared to the wavelength of a light or electromagnetic radiation with which the atom interacts. And typically, the atom is much smaller than this wavelength, and this allows us to make the so-called dipole approximation. And in this case, the atom can be treated as a point-like object, and we don't consider any of the spatial extent of the atom. And to see how well this dipole approximation is satisfied in a variety of systems, because it is almost always applied, it's useful to consider some of these parameters for these different systems. So for example, consider the case of, say, a natural atom, hydrogen, for example, which has transitions that are on the order of optical light. So here, the Bohr radius of this atom, or the radius of many natural atoms, are usually on the order of angstrom. But the wavelength, associated wavelength of optical light is 10⁻⁶, 10⁻⁷. And so the metric that we really care about is the ratio of this radius to the wavelength. And this is much, much less than 1, which goes to show that indeed this dipole approximation is satisfied for these natural atoms which interact with optical light. Now, a lot of my AMO friends like to say that there is a type of natural atom which is physically giant, that being the Rydberg atom, right? These are highly excited states of atoms. And indeed, the radius of these atoms are much, much larger. Like they're now 10 to the minus 7, 10 to the minus 8. But the light that these atoms most strongly interact with are now microwave. And so the wavelength of microwave light is now 10 to the minus 1 to 10 to the minus 3. So if you actually compare the ratio of r to lambda in this case, you're actually deeper into the dipole approximation for the Rydberg atom than you are for, just say, some natural atom which interacts with optical transitions. And finally, to kind of consider a variety of artificial atoms, you can think about conventional transmons. So we have this nice picture of an IBM chip. Yeah, and these interact with microwave light. And so the length scale of these conventional transmons, I say conventional because we're going to make an unconventional transmon soon. So the size of these conventional transmons are typically on the order of hundreds of microns. But again, we're interacting with microwave light. So if you compare the ratio of the wavelength, it's a small typo, it should be the ratio of the x to lambda. This ratio is once again much, much less than 1. So indeed, we're still in this, we're still satisfying this dipole approximation. So the question is, how do we get into this giant atom regime? And the answer is you basically need to somehow make the extent of your atom like on the same order of or larger than the wavelength of the light that it interacts with. And we do this in a very particular way. What we do is we take our atom and we discretely couple it at 2 distant locations. And the important thing here is that each coupling point on its own would satisfy the dipole approximation. However, now because there are multiple, and this separation is on the order of a wavelength, we now need to consider interference phenomenon that occurred due to this propagation phase delay between the 2 points. So there's basically photons in the waveguide will see a phase shift when propagating between x1 and x2 for this atom. And so this is how we will implement our giant atoms. To be kind of more specific, we can revisit the interaction Hamiltonian. And previously, we had this phase factor, which just had the single qubit location. But now we've modified it with this complex coupling amplitude A, which is essentially just sum over all of the phases for each coupling point of the qubit. And you can interpret this kind of a discrete Fourier transform. That's what this term is implementing in a sense. And we'll actually see later on in the talk how we can use this term to engineer some of the spectra in our devices.
Yeah, awesome. Thank you. 2 questions. I guess the second one is about this AJ, but the first one is more about maybe comment/question. So regular transmons, say in a 3D cavity or maybe even in the planar architecture, they tend to be pretty big perturbations, and often beyond the dipole approximation. It's usually, as I've seen. So I guess here a big difference is that in calculating the coupling, you also need to you now have a waveguide, not just a cavity. I think this might apply maybe a little bit more 3D transmon in a 3D cavity, where the structure is quite large and many millimeters across and distributed, and really the mode of the cavity gets highly distorted by the presence of that large giant transmon. And so it kind of reminds me actually of this picture on the right you have, except that it's a cavity, and you can calculate it using eigenmode analysis, for instance, to find out what the coupling is. So
indeed. Yeah, so I guess this is more focusing on the 2D architecture. So 2D transmons with a 2D waveguide, or one-dimensional waveguide. That's the line.
Awesome. And the coupling here is still weak in a sense, in the sense that it doesn't severely perturb the mode structure, the scattering structure of the waveguide, even though it's distributed.
Yes. So I was just about to mention this actually. So we're in the limit where essentially the coupling is weak enough such that it doesn't perturb the kind of the mode structure of the waveguide. And additionally, we're still in this Markovian limit where the emission rate of the qubit into the waveguide is much slower than the travel time for photons to travel between these 2 points, which is why we're able to only account for the interference effect. So we're still Markovian, and this is actually what lets us implement this giant atom in a very clean way. I would argue, which we'll see.
And can you give us a sense of the timescales in the experiment?
Sure. So typically, the coupling to the waveguide is on the order of a few megahertz, maybe tens of megahertz, a few to tens of megahertz. So 1 over that for the emission rate. And then the travel time in between these points is much, I would say, less than nanoseconds. So we're talking maybe hundreds of picoseconds for a aluminum waveguide.
And how do you choose the coupling to the waveguide? Why not make it, 100 kilohertz? Why does it have to be megahertz?
Yes, so this is kind of going back to this point of strong coupling. So we need to make sure that our coupling to the waveguide is much stronger than the other decoherence rates in the system. And typically the primary one, so there's 2 primary ones, one being the kind of the intrinsic relaxation rate of the qubit. This is like losses into the dielectric, for example. But also the dephasing of the qubit. And so this is what kind of sets a lower bound in terms of how low you can make the coupling to the waveguide, but still observe these phenomenon in a strong way. And so we want to be kind of deep in that regime. So we make our coupling strength at least 1 or 2 orders of magnitude higher than those other decoherence parameters.
Okay, yeah, because your I guess T2 phi dephasing rate might be on the order of like 40, 60 kilohertz, maybe up to 100. And
yeah, it'll be like tens of microseconds probably.
Yeah. Awesome. And can you tell us more about AJ and how that, how you determine that and so on, or how that gets? I don't know if you analyze.
I will talk about it more in detail later on in the talk. It'll become clear.
Awesome.
Yeah, great. Okay, so now we've kind of clearly defined what the difference between a small atom is and what our giant atom is, because there's different flavors, as Zlatko has mentioned just now. Okay, so we've done a lot of theory so far, so let's go ahead and look at the actual device geometry for the device that we measure in this paper. So we actually have 2 giant atoms in our that are coupled to our transmission line in our device, and they're coupled in this kind of funky way. We call it a braided configuration because the first coupling point of the second qubit is placed in between the 2 coupling points of the first qubit. And why we have this braided configuration will become clear in just a minute, but for now, that's just what it is. And we have also coupled everything symmetrically in the sense that the coupling points for all coupling points are equal, so it's all strength gamma. And the distance between all successive coupling points along the waveguide are also equal, and the phase delay is just phi. And so here's a picture of the actual device. So you can see the transmon qubits, which are highlighted in yellow, along with the central waveguide, which is in blue, and you can kind of see it meander back and forth between the 2 qubits, kind of in this braided configuration. We also have these flex lines that go to each qubit for independent frequency control. And then we also couple our transmons to cavities in the readout line, standard dispersive readout. Just to quickly zoom in on one of the qubits, you can more clearly see how the waveguide hits both qubits and implements this capacitive coupling between the center conductor of the waveguide and the metal that defines the qubit.
That's a pretty unique and interesting yellow transmon design there. Can you say more about the design choice?
Yeah, so the main consideration here was I basically wanted to make sure the readout resonator was as far as possible from this waveguide so that my readout didn't suffer, because if this readout resonator also coupled strongly to this other waveguide, then that would basically have reduced the lifetime of the resonator and then also reduce the fidelity of the readout. And so basically I wanted to make this resonator as far away as possible. So I have this kind of extension that goes out.
And can you tell us more about the choice of the meters in the blue waveguide?
Yeah, so it's basically just a kind of a coplanar waveguide. And I don't know, do you have any specific question about it, or?
Oh yeah, can you explain why there are these meanders and why there are different sizes?
Yeah, so they're different sizes. So the main thing here is that we have some target spatial separation in order to reach some target phase at a given qubit frequency. And so that's what we're trying to implement here. The reason you see a different, so the lengths here are actually all the same between all successive points. The reason you see the meanders are a little bit different is because these points on the left, or this path on the left and right, have to travel a little bit of an extra distance to go around, whereas the one in the middle doesn't have as much straight path, so it has to meander a bit more. But we actually try to make sure that this device is designed as symmetrically as possible to avoid any issues due to asymmetric coupling or whatnot. And another thing to note here, it's pretty important, is you can see we have these crossovers over the waveguide that are, they're kind of everywhere along the waveguide. And this is very important in terms of suppressing these slotline modes, which can really kind of ruin the physics of the giant atom, hide some of the physics, because you'll have this qubit that's now coupled to this other mode, which isn't ideal. And so these crossovers also play a pretty big role.
Would wire bonds be sufficient?
So I found in my experience that wire bonds are actually not sufficient. Perhaps that's just because I didn't put enough of them, but I found that in devices that have crossovers versus devices that have wire bonds, the crossover ones seem to perform quite a bit better.
Oh,
great.
And I think there was a question earlier which I answered in the chat, but it was, how do you set the spacing between them? So I guess one of them is you actually design the number of millimeters of line. And the other one, though, is that you still have this flux tunability control, so you can sort of maybe also set the spacing by choosing the right qubit frequency. How much range of tuning do you have on the qubit?
Right. So that's a good point. I was actually just about to mention that. So this in the next slide. So this phase depends on both the physical spacing and the qubit frequency of the transmon. And so we can actually change this effective phase by changing the qubit frequency. And what we'll see in the next slide, you'll see how much tuning I have. Good. So the first thing we want to do is measure the properties of these giant atoms individually. So basically just measuring the properties of one while ignoring the other to make things a bit simple. And so this is a schematic diagram of what our chip looked like. And we're just gonna, far detune the second qubit such that it doesn't interact with anything. And that way we can focus our attention on just the first qubit. And we now have this phase delay between these two points of this qubit A that we need to consider. And this phase delay is given by 2 phi, given the geometry shown in the previous slide. And the important thing here is that this qubit is going to be emitting at both of these points. And so we need to consider the interference for photons that are emitted at one versus photons that are emitted at another. And so if you have the condition where this 2 phi, this phase difference, is an odd integer multiple of pi, you're going to get destructive interference between photons that are emitted on one side versus the other. And this will essentially imply that the qubit will not emit into the waveguide. So you can actually suppress relaxation this way. And again, you can also look at the constructive interference condition, where now 2 phi is an even integer multiple of pi, and this will enhance your coupling rate due to this constructive interference. Now, as I just mentioned, this phase delay is tunable. So it depends on the physical spacing along the waveguide, the speed of light v of the waveguide, and the qubit frequency. And this is the parameter. The qubit frequency is the parameter which we tune. And so the first thing we want to do is see if we can actually get to this destructive interference point where the qubit kind of decouples from relaxation into the waveguide. And in order to measure this, what we do is we perform a standard T1 measurement, right? Because we're trying to check how much is the qubit emitting into this waveguide. And so what we do is we simply apply a pi pulse on the qubit to excite it, and then we just wait some period t before performing a readout to measure what the population of the qubit is. And indeed, if we go to the qubit frequency which satisfies this condition, you can see that we measure a maximum lifetime of relaxation time of 31.5 microseconds. And this really is on par with typical flux tunable transmons that are not strongly coupled to an entirely open environment, right? So this goes to indicate that we really are suppressing the relaxation into the waveguide because we're able to get these high lifetimes. But we can go ahead and actually measure the entire spectrum of the relaxation. And so here I'm plotting the relaxation rate. So this is 1/T1 as a function of the qubit frequency, which again is basically just controlling this phase delay between the qubits. And you can see that, okay, we have this point shown in dark green, which corresponds to the destructive interference condition where the qubit decouples from relaxation into the waveguide. But as we change the qubit frequency away from this point, we start to increase, or the relaxation rate starts to increase, which correspondingly means that the T1 will decrease. So this is just a couple of more traces showing how that happens. And to answer Zlatko's previous question, in this particular graph, what we have is phi is varied between 0.9 and 1.1 roughly, 0.9 pi and 1.1 pi. Now we don't actually go to the full constructive interference point with this device because our qubit frequency does not go that high. But the point here still stands because we're able to very strongly decouple our qubit from relaxation and still turn on this emission process at a different qubit frequency. Right.
And you can measure the external flux knob from 0 to 2 pi. I mean, measure the as a function of, sorry.
Yes. Yeah. In principle, yeah, you could measure it. Yeah.
Right. And why in principle, not in practice?
So in this particular, so basically, in order to go from 0 to 2 pi, you need to have the appropriate qubit frequency range. And so the range of our qubit frequencies in this device, we could have gone lower, but the transmon has a maximum qubit frequency. So that's what's limiting.
I got confused because you said 0.9 to 1 point something phi, and I thought you were talking about phi naught.
Oh no, I said pi, 0.9 to 1.1 pi.
Oh, okay, yeah, this is the maximum qubit frequency range, but yeah, so you were talking about the phi on that. Okay, I understand.
Exactly. There's actually another complication arises in the sense that as you go further and further, your relaxation becomes, your T1 becomes lower and lower. And so you actually have to switch from dispersive readout because your qubit has such a low lifetime to a different type of readout, which basically just involves, say, spectroscopy in the waveguide. So there's a few complications there. But the main point that we want to show here is this point where we decouple from relaxation. As I will show, this is kind of the more interesting point.
Nice. And so if you had not 2 red capacitors there, but 3 of them along 3 lines, does that mean that you would still get some interference effect, but never perfect cancellation?
You're asking some very excellent questions, which I will answer. I have slides on this, so.
Right.
It's a great question. We'll get to it.
Awesome.
Great. So we can go ahead and perform a fit to our theory calculations onto our data, just to make sure that what's happening is exactly what we expect. And indeed, we get very good agreement between this fit to theory and the data that we get out. And you'll see that there's this contribution from gamma NR. This is just the intrinsic lifetime of the transmon, which sets this minimum point, this 31.5 microseconds.
And how do you determine phi in this fit, or is that a fit parameter? It's
a fit parameter. So you basically, you can substitute in terms of the qubit frequency, and then this equation now depends. Oh. This equation is now as a function of qubit frequency.
So you know delta x from lithography, yes. And what about the denominator?
So yeah, v has to be fit. Yeah.
Oh, okay, I see. Gotcha. Yeah, but what about doing like an HFSS simulation to find the group velocity of their transmission?
Oh yeah, so we've done that, and you do get it. You can get an answer. You basically can figure out what the epsilon and mu of the transmission line are, and then that will also give you the answer. But typically, there's some variance between what the simulation says and what the fab gives you, because there's always like the width of the center conductor might change a little bit, or the gaps, etc. So we just leave that as a fit parameter.
Mm-hmm. Thanks.
Yep.
Oh, and T2 here, T2 star?
Yes, that's actually a very good question. So there's actually two sweet spots now, in the sense that you have a flux sweet spot, but you also have a waveguide sweet spot where this relaxation is suppressed, right? So T2 has contributions both from dephasing and relaxation. And so we had one device where these two sweet spots kind of aligned with each other, and we were able to get T2 stars on the order of tens of microseconds as well.
And the kind of average T2, so that's the best T2. What about the sort of standard?
So the T2, so as you go away from this point, right, the T2 will then become T1 limited.
Yeah.
So
I guess I mean at the waveguide perfect point.
Yeah, so that simply depends on where you are in your flux spectrum, right? So if this point ends up becoming at a very sensitive spot, your dephasing will not be so great. But in this device that I'm showing here, the flux sweet spot and this decoherence-free spot, which is what we call line up. So we get like 10 point something microseconds for the T2 star. Good. Yeah, and so because this frequency where the qubit has maximum relaxation decouples from the waveguide, we call this the decoherence-free frequency, because you are no longer decohering into the waveguide due to this destructive interference. So I want to actually now take a step back. Before we go to two giant atoms, take a step back to our two small atom case, where we were talking about these waveguide-mediated interactions. And in particular, I want to bring your attention to this statement where I said, even in the condition where we do get some exchange interaction that's mediated by the waveguide, there is still a qubit decay that occurs. And furthermore, if you look at this equation in the bottom, the maximum strength of this exchange interaction is limited at half of the decay rate. So if you really wanted to use this waveguide-mediated interaction, well, you can't, right? Because by the time the qubit excitation would have swapped, most of your excitation would have decayed away. And so the question is it possible to somehow cleverly use giant atoms to get rid of this qubit decay, but still maintain waveguide-mediated interaction? So basically get rid of all the bad stuff, in a sense, and keep the good stuff. And so that takes us now to waveguide-mediated interactions, but now with giant atoms. And so previously with the small atoms, we saw that this interaction depended on the sign of the phase between the points. Now for the case with giant atoms, it's very similar, except we now need to consider the contribution between all pairs of coupling points. So there's 4 in this particular geometry. So this one, and this one, and then one formed by the first and last point. And because the distance between these two, or the phase delay between these 2 points are all phi, the contribution from these 3 consecutive coupling points will be gamma over 2 sine phi, very similar to the previous slide. But we also have the contribution from the first and last point, and that's going to give us a sine 3 phi, because there's 3 phi in between. And in order to figure out what the net interaction strength is, you basically sum up all of these components, and so you get 3 sine phi plus sine 3 phi. And in order to measure this, at what this exchange interaction strength is, we perform qubit spectroscopy and measure the avoided level crossing formed when the 2 qubits are, where one qubit is swept onto resonance or past resonance with the other. And then the splitting, the splitting essentially tells us what this G is. And we can go ahead and do this as a function, once again, as a function of qubit frequency. And what we find is a curve that matches what our theory predicts. But the important thing here is if we look at this frequency, this decoherence-free frequency, we still have a finite exchange interaction. So what this means is that we are able to suppress the dissipation into the waveguide while maintaining this interaction that's mediated by the waveguide. So this is kind of what we were trying to do. And we call this a decoherence-free interaction because, again, you protect against decoherence into the waveguide while still maintaining a finite strength. And this is a little bit counterintuitive because most people would think if you decouple from the waveguide, you would also lose the interaction that it mediates as well. But it turns out because these are mediated by these virtual photons, you can get one while getting rid of the other. Now, as Zlatko alluded to with one of his questions earlier, we can actually take this one step further. We can think about engineering the coupling spectra with giant atoms. And there's a few kind of parameters that we can play with. The first one being the one that he mentioned. You don't need to limit yourself to just 2 coupling points. You can think about n coupling points, right? 3, 4, 5. And so if we just take a very simple, take a look at an example. So this is what the relaxation rate as a function of phi would look like for n equals 2. So this is what the device that we had before would look like. But now if we consider geometries with more than 2 coupling points, you can see that as I increase n from 3 to 4, you can really start to engineer how this spectrum looks. And indeed, although the interference conditions are no longer as simple as just odd or even integer multiples of pi, but there are still points of constructive and destructive interference that occur. And we can also vary the relative coupling strength between these coupling points. So previously we had all of these be symmetric, so all be the same gamma, but now we can think about changing the relative coupling strengths. So this is again just showing this relaxation rate for different relative coupling strengths for an n equals 3 giant atom. And once again, you can see how we're able to change the shape of the spectrum by changing this ratio. And finally, we also have some control over what the phase or distance between these coupling points are. So in the previous device, they were all set to be equal, but this need not be the case. We have some control over that in terms of how we engineer the device. And so we can really think about putting all of these control knobs together to perform or create some sort of application that we want to do. So to that end, we actually went ahead and created this n equals 3 giant atom. So now the geometry is still braided because it turns out this braided configuration is the only one where you can get a waveguide interaction, but no dissipation. So we have n equals 3 braided giant atoms, and you can see the geometry is a bit more complicated. So we have different phase delays between these points now, but there still is a degree of symmetry, mirror symmetry, I guess. And this is what the device looks like. So it looks, a bit more beastly, I guess. And you have these meanders that are much longer and go back and forth and back and forth. But at the end of the day, if you just take a zoom in on the atom itself, you can see how it couples to 3 different points. And we're able to control the ratio of this gamma 1 and gamma 2. So the first and last points are coupled equally. They're both gamma 1. But the middle point we couple stronger just by basically increasing the capacitance to that point of the waveguide. And now the question is, okay, why, we can do this engineering, but why would you want to do it? Oh, and here's just some parameters. So we've chosen phi 1 equals phi 3, which is half of phi 2, and then this gamma 2 is about 3.5 times stronger than this gamma 1. Yeah, and you can see here that we're able to actually, with this device, engineer a spectrum in the relaxation rate where there are 2 coherence-free frequencies. And this is all while simultaneously maintaining this finite exchange interaction between the 2 qubits. So we have the relaxation rate shown in blue, and then the exchange interaction rate shown in red. And what this lets us do now is we can essentially place one qubit at one decoherence-free point and place another qubit at another decoherence-free point, such that the interactions are suppressed and the dissipation is suppressed. So we have control over both in a sense now. And now we can think about actually trying to perform some coherent quantum operations with giant atoms, in spite of the fact that they are very strongly coupled to a dissipative environment being the waveguide. And so what we do is we place one qubit A at the lower decoherence-free point and qubit B at the upper decoherence-free point. We apply a pi pulse onto qubit B, and then we bring qubit A onto resonance with qubit B and let them interact for some time t, because waveguide is mediating some finite interaction between the qubits. And then we can perform readout to see what happened in the end. And indeed, when we do this measurement in the time domain, you get the standard chevron pattern showing the swaps between the two qubits, indicating this exchange interaction. And if you look at the point where the qubit A is brought exactly onto resonance with qubit B, you can see the exchange of the excitation back and forth between the two qubits. And now we can actually pause the evolution at a quarter period by detuning the qubits again, so bringing them back to their two decoherence-free points in order to prepare some kind of an entangled state, in this case, just 0, 1 minus I 1, 0. And we perform 2-qubit tomography to indeed verify that we've prepared this entangled state, and we get a fidelity of about 94% for this state preparation. So this is just to show that even though we are coupled to this open environment with giant atoms, you can think about still doing these coherent quantum operations mediated by these long-range interactions from the waveguide. And now to think about what's going on, what we can do even further. It turns out you can even engineer the connectivity between the qubits in the waveguide. So this isn't something that we've done yet, but if you, for example, want to implement a Ising spin chain with nearest neighbor interaction, so this would be the most natural extension of our work, you would want some coupling that looks like this. Then if you were to draw the schematic along a waveguide, you would basically just have successive braided giant atoms. And then if you were to actually draw a geometry for what it would look like in real life, you would just have this meandering waveguide with giant atoms placed back and forth. And these figures are from the theory paper, which our work was based on by Anton Koch at Chalmers. But you can actually do all-to-all interactions with these waveguide-mediated interactions as well. So here, for example, if you wanted 3 qubits all-to-all, you would need some kind of geometry that looks like this, where one qubit is braided with both qubits. But if you were to draw what the geometry would look like in real life, you can see the topology is a bit different. You now need to have the waveguide hop over itself. But I mean, this is with 3D integration or crossovers, this is not entirely impossible. But this just goes to show that depending on the geometry of the device, not only can you engineer the spectra, you can engineer the connectivity of the interactions between the qubits. So with that, we can now do a little bit of outlook. So we've realized a rather novel regime of light matter interactions, and we've done it in a, I would say, a very clean way. We're able to get these decoherence-free frequencies, and our theory matches very well with what we expect from experiment. And we've also showed kind of how to engineer these qubit waveguide and qubit-qubit couplings via the device geometry in order to, for example, perform some coherent quantum operation. And now a bigger picture, when do these high fidelity coherent operations on qubits, when are they useful, particularly for qubits that are in the presence of a waveguide? First of all, as I mentioned, this can be applied towards these itinerant photon generation of non-classical photons. And this can then be applied for creating these sort of quantum interconnects if you want to try and communicate between cross-chip, 2 quantum chips. We can also think about these long-range interactions with engineered connectivity, particularly in the context of maybe doing some sort of quantum simulation of spin models or certain field theories that involve some kind of bosonic bath. So, for example, maybe some fermion boson coupling type experiments. That's one of the things that we're actually thinking about. And yeah, with that, I would like to acknowledge all of my collaborators, both at MIT campus and Lincoln Laboratory, with a particular shout out to Max, who was he was a visiting master's student who worked very close with me on these experiments, and Anton, who was the theorist that guided us along these experiments. And yeah, thank you very much.
Thank you so much. This was a really great talk with some very exciting and awesome results. So congratulations to you and the group, by the way, on the really great results. And
thank you very much. Yeah.
We had a lot of questions during the talk, so I know we're almost, I think, 2 minutes over, but that's totally quite fine. So unless I see any further questions from the audience in the chat, okay, we do have some. So question from Sashkant: are there plans to use the subradiant states for quantum memory applications?
Yeah, so there are some people who are working on, they're called decoherence-free subspaces. So using these dark states, which have very long lifetime, for some kind of quantum computation. So this paper that I mentioned with these atomic cavities, they show how you can actually perform perform operations with these dark states. Yeah.
Okay, wonderful. And I don't see any other questions, but you do have a lot of comments. You can look, and I am sorry, more questions popped in. Have there been efforts in simulating spin waves? Yet just want to see how the choice of transbonds compares with, say, other systems.
Could you repeat the question? Sorry.
This is a pretty specific question, so I'm not sure if we know off the top of our heads here, but have there been efforts to simulate spin waves with any of this? I guess this might be down the line.
My guess is this is talking about with some of these Ising models, perhaps. Yeah, I'm not aware.
Gotcha. And is it useful to think in terms of three-dimensional interaction between the waveguides?
Three-dimensional.
I also didn't understand that question, so feel free to clarify, Jeremy Wing.
So I would say it's okay. Maybe I'm not understanding the question, but one of the important things here is the fact that our waveguides are one-dimensional. This is kind of what allows us to enter this strong coupling regime, because in one dimension, these vacuum electric fields are much larger, and as a result, the interaction strengths are also correspondingly larger. And especially because in Waveguide QED, compared to cavity QED, where your coupling strength gets enhanced due to the closed nature of the cavity, right? In Waveguide QED, because you don't have this photon that kind of sees the qubit multiple times, it just sees it once, you don't get that enhancement. And so reaching the strong coupling regime is much stronger. And so it's important, I think being in 1D is one of the benefits which allow us to enter this strong coupling regime with ease. Mm-hmm. Too many tricks.
And this is a question from Nele, would 3D integration pose any problems for coherence and lifetimes of the qubits?
I would say, so I guess they're talking in the specifically in the context of this Waveguide QED work, I would say 3D integration would be quite useful, because now we don't have to waste space on the qubit chip for the qubit, for the waveguide to do the meandering. We could do that on a different layer. And that could be very useful in terms of actually implementing these long-range interactions between the qubits. I think in terms of, in general, 3D integration, there's been work that's shown that qubits don't really suffer that much in terms of coherence times.
Okay, wonderful. I think there may be one or two questions I missed, so I apologize. But overall, I think we will thank you for giving this wonderful talk. I will point out that a few people in the comments here have said that you had a great delivery, very clear, and we're very thrilled to have you. So they said, awesome.
Thank you very much.
So thank you guys for giving feedback. That's always very nice to hear and very helpful. Yes, I want to thank you, the audience, for joining us today. I want to thank you, Bharath, of course, for the wonderful talk and great results. I will leave it up to you if you want to say any final words or comments. I think you're also on social media, so people can connect if they're interested.
Yeah, I want to thank all the viewers, I guess, and I'm on Twitter, so you can, if you have any further questions, you can just tweet me.
Wonderful. All right. Well, with that, thank you everyone for tuning in to the Qiskit Live seminar. We will see you next Friday at noon Eastern Time with another great talk. And thank you very much, Bharath, for joining us today. And we will have more talks from your group, I think, coming. And I think Will be coming on the seminar not too long from now. So
Great.
forward to that as well. And thank you, everyone. We'll see you next week.